Woohoo! Another test! Another chance for us to show our skills and how much we've learned. And what a wonderful test this is. Calculus 1, Math 165, the final home stretch. We do a little bit more with our applications of derivatives and starting to get into integrals. Life is good. It's a wonderful test. 7 problems for us to look forward to. We put down our name. Of course, for us, we're answers, and we're ready to begin. So let's get going. Number 1, evaluate the following limits. So, two-parter. Part A, find the limit as x goes to 2, sine of pi x over x squared minus 4. And your final answer should not contain any trig functions. All right, well, let's see what happens, right? So whenever we're doing a limit, the first thing is we say, well, what happens if we plug in our point? So let's see, sine of pi x over x squared minus 4. What's it going to? Well, plug in 2. Sine of 2 pi. Now, if you think about a circle, of course, behaves like a circle. So 2 pi is like we're back where we started, and the sine is the y-coordinate. So sine of 2 pi is 0. Downstairs, 2 squared is 4. 4 minus 4 is 0. Aha! So our answer is 0 over 0. No. That's never an answer. 0 over 0 means what? More work. More work. All right. Well, what do we need? We need l'hôpital. All right. So let's, of course, we always come prepared, right? So, l'hôpital, mon ami. All right. We are ready. All right. So how does it work? So if we're going to 0 over 0 now, it's really special, has to be 0 over 0. Then what we can say is by l'hôpital, then this is the same as the limit as x goes to 2 of what? Well, you take the derivative, but not like quotient rule. It's the derivative of the top over the derivative of the bottom. Now, I'm partial to the bottom because that looks easier. 2x. All right, derivative of sine is cosine. And so we have a cosine pi x, and then chain rule says take the derivative of the inside, so you put in a pi. All right, good. Now, what happens? Well, we're going to plug in 2. But do you see how the denominator is 2 times 2, which is 4, which is not 0? So that's it. Game over, man. Game over. As soon as we know we're not going to get a 0 over 0, we just plug it in, and whatever it is what it is. All right, so downstairs 2 times 2 is 4. Upstairs we have pi cosine of 2 pi. But wait, we just said 2 pi is going all the way around. And we're back where we started. So it's like cosine of 0. And cosine of 0 is 1. So you get pi over 4. Done. All right, well, with part A, but of course there's more. This one, there's a part B. So, part B, the limit as t goes to infinity. 1 minus 2 over t squared to the t squared. Okay, well, before we do anything, what do we see? Well, t is downstairs, so this is going to get very small. So the inside is going to a number close to 1, and the outside is going to a big number, infinity. All right, well, what is 1 to the infinity? 1? Actually, this is, again, indeterminate. And, well, what does that mean? Well, it means more work. But we're not ready for l'hôpital. Oh, sacre bleu. I mean, what's wrong? We don't have a 0 over 0. If it's not 0 over 0 or infinity over infinity, no go. Nothing doing. Can't do it. So what do? Well, we change it. So let's, for a second, let's suppose we call this y. You might say, well, why not? Well, we could add a why not there, but let's just call it y. And we want to bring this numerator down. So that gives us a shot. So we're going to use log of y Okay, and the nice thing is limits pass through continuous functions, and log is a continuous function, so we can pass it through, and we get the following. This is the limit as t goes to infinity of log of 1 minus 2 over t squared to the t squared. And now we start using properties of logs. The exponents can come down. Good. So that's the limit as t goes to infinity of t squared log 1 minus 2 over t squared. Now we can pause for a second and say, well, what's happening to this limit? Because is it ready for us to do l'Hopital? Well, we can see no. Why? Well, there's no fraction. But we say it's getting closer, right? So this part's heading towards infinity, and this part's heading towards log of 1, which is 0. Okay, that's better, closer. But we need to move something downstairs. Now, we have two things we could move. Which one should we move, and why is it the t squared? Okay, so it is the t squared. But why? Well, for that, what we say is, look, we want to have whatever we take a derivative of be simple. Log is already complicated enough. Let's not overcomplicate things. So let's move the t squared down. All right, so we can move this up. So we have that this is the limit as t goes to infinity of, and we're going to have upstairs log of. Now, we can do a couple things here. Notice this is a log 1 minus 2 over t squared. You know what? Actually, let's just leave it. I think that's going to be fine. 1 minus 2 over t squared over t squared. 1 over, right? It's not you move it down. You have to flip it when you move it down. So it's 1 over t squared. Okay, now we're going 0 upstairs, 0 downstairs. Life is good. So, l'Hopital, mon ami. All right, so we apply l'Hopital, and we take the derivative of both top and bottom. And of course, the derivatives are more complicated, but we're not stressed. This is just l'Hopital. Life is good. So upstairs, log 1 over the inside, and then times the derivative of the inside. Well, that's minus 2 over t squared. Right, derivative of 1 is 0. So we have a minus 2 coming out. And then 1 over t squared we can think of as t to the minus 2. So that would become minus 2 times t to the minus 3. Now downstairs, again, that's t to the minus 2. So we have a minus 2, and then a t to the minus 3. And now we say, things simplify, because we can cancel. And what do we have left? Well, at this point we have the limit as t goes to infinity of minus 2 over 1 minus 2 over t squared. Wonderful, right? The over t squared part goes away because it's going to be really big as the t squared, so over something big is small. So we get negative 2 over 1. All right, brilliant. Is that our answer? No. What? 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 Why? We worked so hard. Well, follow it back. It's the log of our answer. And so therefore, our real answer is y is e to that. So it's e to the minus 2. And done. That's it. Beautiful. L'Hopital. So good to see you. And hopefully we will get to see you again someday. All right. Well, on to the next problem. Number 2. We're going to use Newton's method to estimate the x-coordinate of an intersection point of the graphs of y equals 2x and y equals x squared minus 1. So we're going to start with x0 equals 0 and find the value of x2. And it says simplify your answer to an integer our single fraction. So in other words, clean it up. Now there's a couple of things. What is Newton's method, and how do we apply it here? So the idea of Newton's method is what? Well, it's about finding roots. That's the goal. And how does it work? Well, it says, look, if you have a function, and so your goal is, I want to find this is the special point. You say, well, I make a guess. And I say, all right, here's a guess. And now, you say, okay, well, that's wrong. Can you make a better guess? And the answer is yes. You make a better guess by saying, follow the tangent line. The tangent line will take you to a point closer to the one you're after. So if you work it out, so if this is the curve, say y equals f of x, and here is our current guess, so that's at the point x sub n, f of x sub n. So just the subscript says, what's the number of my guess? So we start with an initial guess, we improve it, we improve it, we improve it, and then what works out is you say, well, the tangent line would be y equals f of xn plus f prime of xn, x minus xn. Now, we're after that point. What's special about that point? It's at 0. So, you say 0 is equal to f of xn plus f prime of xn times, and this is the key, what our next guess will be, minus xn. And if you just rearrange that, you say that our next guess is our current guess plus a correction. And to find the correction, you subtract and divide, so minus the function over the derivative. Okay, so this is the rule. All right, great. Now, at this point you say, okay, Steve, that's all well and good if you're finding roots, but notice it doesn't say roots, it says intersection. Well, what does it mean to say find an intersection? Well, it says, when do these two equal each other? Okay, so idea. We can move one thing across. Now, it doesn't matter which we move across, but then we can say, well, this is the same as finding when does 0 equal x squared minus 1 minus 2x. So, our finding intersection is the same as finding a root. Okay, so this is what we're going to call our f of x. And so our rule, well, we need to work it out, right? It says that our next guess is our current guess minus our function of x. So that's xn squared minus 1 minus 2xn over our derivative. Now, we can actually work out the derivative really quickly. That's f prime of x is 2x minus 2. Right? 2x goes away, minus 2. So 2xn minus 2. All right, good, good. Now, the fun part. So we know where we're starting, x0. We know where we want to get to, x2. So we say, all right, x0 is 0. So our next guess, x1, would be x0 minus x0 squared minus 1 minus 2x0 over 2x0 minus 2. But each place where there's an x0 is a 0, so those will all go away. So in fact, that goes away too. What do we see? Well, we see a half and a minus. So this becomes minus 1/2. All right, good. So that's our first iteration. Our second iteration, x2. Well, that's x1 minus x1 squared minus 1 minus 2x1 divided by 2x1 minus 2. All right, we have to do a little bit more work here because 0 was a very convenient number. It's one of our favorites. Minus a half minus, okay, minus a half squared would be a fourth, minus 1, minus 2 times minus a half, well, that becomes plus 1, right? 2 times a half is 1, and 2 minuses make a plus. Downstairs, 2 minus a half times 2 is minus 1 minus 2. Well, okay, so those cancel. Downstairs we have minus 3, and minus minus makes a plus, right? So factoring the minus out. So there's a fourth over a third, makes a 12th. Well, if we add these up, that'd be minus 6 over 12 plus 1 over 12, which is negative 5 over 12. Because we did have to simplify it down to a fraction. And there we go, minus 5/12. That would be our second guess, and probably not a bad guess. Of course, in this case, we can find it exactly because we have quadratic formula. But if we found the quadratic formula and applied it, we wouldn't get any points, because that's not what it asked us to do. It asked us to get an approximation. And there we have it. Life is good. Life is wonderful. And we're ready to keep moving on. Number 3. Let f of t be a continuous function defined for t, and t goes from 0 to 8.5. And we're asked to approximate the following integral. Integral 2 to 4 of 2 f of 2t dt. All right, good. Now what's going on? Well, we're approximating, so we're not finding it, we're approximating it. And it says use a Riemann sum. So the idea is I have some curve doing something, I don't know, but I have a few pieces of information. We're going to go from 2 up to 4. And then it says, okay, 4 equally spaced interval. So you cut it into 4 equal parts. And then you use the left endpoints of each interval. Now, what is this doing here? Well, this is telling us how to find the height. See, the width is easy because we know it's 4 equal parts. We're going from 2 to 4, so each part has to have width a half, right? You can just sort of see it 3, here's 2.5, here's 3.5. It's the width is half. So the endpoints are going to help us get the height. So the height, we plug it in. So we're going to use our table to figure out the height of each rectangle. All right, so how do we do it? Okay, so here we go. We know, and again, we know our left endpoint, so we'll draw this a little bit more carefully, or perhaps I should say a little more legibly. 2 to 4, so we have 3, 2.5, 3.5. The widths are a half, so our Riemann sum is a half, and now we plug 2. Now, do we plug 2 into our function? Kind of. Be careful here. They're checking if we're paying attention, and we don't want to lose points. I mean, our goal is to get all the points. Got to get them all, right? So we're plugging them into this expression here. All right, so I'm going to plug it in 2 into here. Say, okay, well, what does that give us? Well, it gives us 2f of 4. Okay, then a half, going to our next one. Now we're going to plug in 2.5, okay? What does that give us? Well, that's going to give us 2f of 2 times 2.5, 5. And then another half, and we're going to plug in our 3. Okay, so we have 2 times f of 6 plus a half, and finally, when we plug in 3.5, what do we get? Well, we're going to get 2f of 7. Now, the nice thing is the halves and the 2's all cancel. And so what do we really have here? Well, we have f of 4 plus f of 5 plus f of 6 plus f of 7. Well, okay, so we start reading that off. That's 10, 12, 20, and 22. Good. So let's see, that would be a big number. We can figure this out. That would be 62. Well, no, 64, right? if we add the 1 digit, that's a 4. And then we have the 10 digits, we get 64. All right, good. So that's an approximation for the area. All right, well, that's nice. But there's a second part. Okay, good. What's the second part ask? Part B. Given that f of t is monotonic increasing, that just means it's going up. It goes up. Is your approximation in part A an overestimation, underestimation, or not enough information to determine? And choose one answer. No explanation needed. Well, we don't have to justify it, but we should explain it to ourselves. You know, we have an internal dialogue, and as we listen, say, well, look, f of t is monotonic increasing, and so if we come back up here, notice we're actually not integrating f of t, but 2f of 2t. Now the 2 will stretch in this way. The f of 2t will actually be a compression this way, but the moral is, if I am indeed going uphill, then what will happen is, if I stretch and I squish, I'm still going uphill. So I say, aha, if I'm going uphill, then when I find my little rectangle, what I see is I'm off and I'm missing a piece. So I'm missing the little piece on the top. So what does that mean? Well, it means that the rectangle, which is my Riemann sum, doesn't capture everything. It comes up just a little bit short. So each rectangle is just a little bit under what it should be for that portion. And so each one being under means that altogether we will be under. And so we see that our answer is going to be an underestimation. And that's what's going on. Part B, done. Good. All right, we're ready. On to the next problem. Number 4. The graph of the function f of x on the interval -4 to 4 is shown below. And it says, note that on -4, 0. Now this notation means here, this is an interval. And it says, starting at -4 and going to 0. So this piece right here, it's a half circle. Okay, so this is, it's not a parabola, it is truly a half circle. Okay, so a half circle, a line, and a flat line. All right, good. All right, so we have questions. Well, that's great. We have answers. All right. If f of x is the integral -4 to x of f of t dt, and g of x is the integral -4 to x of absolute value f of t dt, determine the following. All right, so part A. So find f of 4. Okay, so this is, we're going -4 to 4 of f of t dt. Okay, so we come up to our picture, we're going -4, +4, and we just need to do some counting. So we can split our shape up into a couple pieces. We say, okay, well look, we've got a rectangle here, got a half circle here, got a little triangle there, a little triangle there, and a rectangle there. So in other words, we're using geometry. So this rectangle would be a 1 by 4. So that would be an area of 4. But notice it's downstairs. An integral is signed, so we can have positive and negative. So we have a -4 plus, now this is a circle of radius 2. And because, well, it tells us radius 2. And we're taking half of them. So because we're downstairs again, we'll have a minus, but then we have half of a circle of pi r squared. Now we come here, there's a little triangle, but it's below, that's a minus, and so that's minus, well, 1/2 base height, so 1/2, 1, 1. Here, there's a triangle, 1/2 base height, so it's a 1/2, 1, 1, but now it's positive, and finally there's a little 1 by 2 rectangle, so that's a +2. All right, well, what happens? We clean some things up. So these cancel, which is great. 2 minus 4, would give us a negative 2. This minus will stay a minus. The 2 goes into 2 squared. That leaves us with a single 2. So we're going to have a minus 2 pi. Okay, it's a negative answer, but it's not surprising it's negative because there's a lot more area below than there is above. So we should expect a negative. All right, good. That's part A. Now we go on to part B. It says find g of 4. Well, we just literally put in where the x should go, so that's negative 4 to 4 of absolute value of f of t dt. What's the difference? Well, the difference is this part's going to flip over. Same geometry, now just all our pieces are positive areas. And so no cancellations. So we have our pieces. So we have 4 plus a half plus a half plus 2. That would be 7. And then a half times 2 squared, or 4, that would be 2 pi. So 7 plus 2 pi. And there we go. See? Once you know the geometry, you just say, pay attention to the signs. What's the sign? Okay, part C. Find f of 2 minus f of 0. Okay, so let's just write what f of 2 minus f of 0 is. So that would be integral negative 4 to 2 of f of t dt minus the integral from negative 4 to 0 of f of t dt. Now, here we can use properties of integrals to say, oh, well, what are we really doing? We're taking the integral from negative 4 to 2, but then we're subtracting out the integral from negative 4 to 0. This is the same as going from 0 to 2 of f of t dt. And we say, okay, going from 0 to 2, what do we see? Well, we see a negative piece, a positive piece, but they're equal area. They'll cancel out, and we get 0. That's that one. See, once you understand, it's all about grabbing the geometry of the picture, which is the right piece to grid, life is good. And we say, okay, what about our next one? Well, it's going to be very similar, right? Except now it's g, but everything else follows through. The only thing that's different is we get absolute values. So again, we can say, well, look, these two pieces combine. We can say this is the same as going from 0 to 2 of absolute value of f of t dt. And now, instead of having a negative and a positive cancel out, when it flips to the other side, right, because this is, we could even sketch in what happens when we flip. When we flip, it's a positive a half and a positive a half. And they come together and they give us 1. You can think of it like the two triangles just doop, and you form a nice 1 by 1 square. All right, good. Now, our last piece. Okay. And this one, well, it's a little different because it involves a derivative. So we have g prime of minus 2 minus f prime of minus 2. Now here's the thing to remember. When we do a derivative of an integral, what happens? Well, what happens is that we have something fun, very fundamental, the fundamental theorem of calculus. So we say, okay, look, g prime of x is, since there's nothing fancy, it's just x, that'd be absolute value of f of x. And f prime of x, well, again, it's the function on the inside, that's f of x. So if I want g prime of minus 2, subtract f prime of minus 2, this is the same as the absolute value of f of minus 2, subtract f of minus 2. Okay, so we come down, come up to our picture, say, okay, now at minus 2, our value is negative 3. So this would be the absolute value of negative 3. Subtract negative 3. Well, the absolute value gets rid of the negative. Minus minus becomes plus. So you really have 3 plus 3, which makes 6. So our answer is 6. And we're done. We found all our pieces. And so nothing too surprising. Use geometry, use fundamental theorem of calculus. Life is good. Life is wonderful. All right, I think we're good. Let's move on to our next problem. Number 5. Let f of x equal 4 plus the integral of 1 to x squared of 2t squared plus 1 over the square root of t squared plus 3 dt. What? That looks terrible. Maybe we could do that next semester, but how do we integrate that today? Or do we even have to? Probably if something looks really hard, maybe we don't have to do it. I mean, sometimes we do, but let's see what's going on. First thing, f prime of x. All right. Good news. We know how to find derivatives, and in particular, we can say, great, there's actually going to be two things going on here. We have the fundamental theorem of calculus, which we'll abbreviate, fundamental theorem of calculus. And then we're going to have one other thing thrown into the mix, and it's called a chain rule. Now you might say, wait, what? Why are you throwing in the chain rule here? Well, if you look closely, there's something interesting going on. Now the fundamental theorem of calculus says the derivative of an integral is more or less the function on the inside, but that's if we're integrating from a constant to x. We're not going from a constant to x, we're going to a constant up to x squared. But that's all right. We still have our basic thing. And so if you write the fundamental theorem of calculus plus the chain rule together, you can say it's the following. That says the derivative of the integral from some constant c to g of x of f of t dt is equal to f of, plug the inside function is g of x, so plug it into the derivative. So normally the derivative would just be f of x, so it's f of g of x, and then times on the outside by the derivative. So that's what we're going to be using in our toolbox to take our derivative. All right, so here we go. Now, derivative of 4, 0. Don't forget it. At least don't forget to take the derivative. You might say, oh, just write the 4 down again. No. Got to take the derivative of each part. So, okay, so f prime of x. So according to this, we're going to plug x squared everywhere where we see a t. So we're going to get 2x squared squared plus 1 over the square root of x squared squared plus 3. Notice the use of parentheses. Parentheses are your friends. They will save you points. We want to use them. All right, now that's the f of g of x. Don't forget the g prime. So times by 2x. And then we can clean it up. That's the answer, but we can be nice. So x squared squared, so that becomes x to the 4th. You can multiply the 2 times the 2. We have a 2x to the 4th, and then we'll multiply that by 2x. So that'll give us 4x to the 5th. 1 times 2x is 2x. Over, downstairs, we get square root. X squared squared, again, is x to the 4th, and plus 3. And there we go. Nice. Good. Okay. Now, that was part A. Part B. Well, part B says, find the equation of the tangent line to the graph of y equals f of x at x equals 1. It wouldn't feel like a Calc 1 test if there wasn't a tangent line in there. So it's good that we saw one. Okay, so how do you find a tangent line? Well, the basic formula is you would take f of 1 plus f prime of 1 times x minus 1. So the key is, what are these numbers? Now, f of 1, let's talk about that. That looks hard, but if we just plug in everywhere where we see an x, you put a 1. Well, there's only one x. So there's the integral 1 to 1 of 2t squared plus 1 over the square root of t squared plus 3 dt. Now, okay, the 4 we know is the 4, but how do you integrate this integral? Or do you have to? Notice the bounds. When the bounds match, that says there's no width. No width, no area. No area, 0. So that goes away. So f of 1 is 4. What about f prime of 1? That's what we spend all our time in. We say, look, go to part A. So everywhere you see now an x, put a 1. We're going to get a 4, and 1 to any power is 1. 4 plus 2 over the square root, 1 plus 3. Now, that's square root of 1 plus 3, square root of 4, which is 2. Upstairs we have 6, so we have 6 over 2, which is 3. And so, our tangent line is 4 plus 3, x minus 1. And we're done. Because that's all it asks. And it only asks for the tangent line. In some sense, I think the little key here is they are testing us on, do we know how to first off say, what is f of 1? What is that expression? And do we understand if the bounds agree, the answer will flee? Oh, wait, no, that's not how it goes. But the answer is going to be 0 when the bounds agree. And that's what we have. And so, wow, great. That's a fun question. Let's hope for one of these on the next test, right? Well, maybe. You never know. Or maybe you'll know really soon. All right. Well, we're almost done. Just a couple more to go. Number 6. Compute the following integrals. Wonderful. And we don't just have one, we get 2. Lucky day. And we stare a little bit closer and we see that actually they're kind of different flavors. This first one, there's no numbers. Now that means it's an indefinite integral. You might also call it an antiderivative. And so this one, we're going to have the answer be a function. Now whenever you have an indefinite integral, don't forget plus c, because they're going to take off a point if you forget it. We want all the points. Got to get them all. Got to get them all. Now this integral has bounds, numbers. So this is not going to be a function. It's actually going to be a numerical value. And so make sure you know, should I have a function at the end with a plus c or a number at the end? And if it's a number, there's no plus c. C need not apply. All right, well, let's start with the first one because I can already tell, and I'm getting a little emotional here. There's an arctangent, and I love arctangent. It's the coolest function. Okay, all right, okay. So what do we do? Now, well, we say, look, kind of hopeless the way it's written, right? Square root of arctangent, but that's all right. We have our ways. And so we also start to say, we come to the bestest tool when it comes to integration. So I think that this question is really getting at this notion of what's called substitution. Substitution is the go-to method of simplifying integrals. And what we're looking for is functions in functions, right? Substitution is an inside job. Now, you see there's an arctangent inside a square root. So we say, idea. So first off, I'm going to write this in a slightly different way. When I'm writing things to be calculus friendly, I tend to get rid of the square roots, and not that I'm removing them, but rather I'm expressing them in a different way, to the 1/2 power. Because that falls into our rules. All right, now, what's the inside function? The inside function is the arctangent. So we say, okay, great. We're going to let u equal arctangent of x. And then we say, what's the derivative of arctangent? Which, of course, all together, 1 over 1 plus x squared. Yes, yes. And don't forget the dx. Yes, that's part of the derivative. And we say, almost as if it was meant to be. because I think it was. That's our du. So this part becomes our du. Okay, so what do we have? Well, so this becomes the integral. We have the 3. Arctangent of x to the 1/2 becomes u to the 1/2. And then the rest of the pieces becomes du. And now life is good. The 3 is a constant, so it can come out. So we have 3. And because we have it as u to the 1/2, that's our calculus friendly in that it really fits into the rules. So what do we do? Well, we add 1 to the exponent. That becomes 3/2. Now remember, you have to multiply by something in the front. And this is where it can get tricky. Do you multiply by 3/2? Do you multiply by 1/2? Or something else? Well, it's actually something else. You take your exponent and you flip it. So if it's 3/2, 2/3. And you wait till after you add it. So 2/3. And remember, we said, don't forget the plus c. They're going to be watching you. They're going to be looking. Did they get the plus c? And did they put it in the right places at the right times? All right, so the 3's go away. And you might say, great, we're done, right? Well, no. We introduced. The problem didn't. So we've got to work backwards. So how do we work backwards? Well, we say, well, what is u? It's arctangent of x. So we have arctangent of x to the 3/2 plus c. And done. Nice. Ah, lovely, lovely. Okay, so next up, on to part B. The integral from 0 to pi4 of tangent of x plus sine of x e to the cosine x. Now, we could do something, it's perfectly legal, which is to say, this plus, it allows us to separate it into 2 pieces. So we could do the integral of tangent x, and we could do the integral of sine x e to the cosine x. We could do them separately, see what they look like, compare, and then if we're happy, great. And if we're not, well, whatever. Or we can see if maybe the same thing works for both. Now, tangent of x, we can ask the question, do we know the integral by heart? You may actually. It is ultimately one of a handful of integrals that you should learn. But if by perchance you haven't, let's just figure it out. So we say, hey, do we know it? Like, no, I forgot it. Oh no, woe is me, for I am undone. No, you're fine, no worries. What you do is say, okay, what's another way to think of tangent? Another way to think of tangent is sine over cosine. Say, oh, okay, well, how does that help me? Well, notice sine and cosine are closely related to each other. In essence, one of them is the derivative of the other. And so we almost have a function downstairs, derivative upstairs. And I say almost because there's a minus sign missing. When you're in that situation, function downstairs, derivative of the function upstairs, that's a happy place to be in, because that's a good substitution. In that case, you make your substitution is the downstairs. Now, if you come to this part right here, you see how we have that e to the power cosine x, e to the cosine x? Well, what does that mean? Well, that says our cosine x is our inside function. And so we say, oh, in both cases, we should be thinking of letting u be cosine x. And in that case, the derivative, well, that's minus sine of x dx. Well, okay, so what's going to happen? Well, we're going to get the following. We have the, we will, hold on a second before we carry the substitution all the way through. So we have a sine of x over cosine of x plus sine of x e to the cosine of x and dx. Now, we see, okay, the sine of x, the dx, almost becomes du. We just need to put a minus sign. And so we say, okay, so we'll put a minus 0 to pi4. Then we have the cosine of x has become u. So there's a 1 over u. And then that's gone. because that's part of our du, and plus e to the u and du. Now, am I right? Well, I've done a flub. A flub? A flib? I don't know. I've made a small, tiny mistake, right? But that's all right. I'm going to catch it. Notice these bounds. Now, what we oftentimes don't write what the bounds are, these are x bounds. So here, these bounds, I didn't change them. They're still x bounds. So what's the problem? We want our integral in terms of u. So we should actually fix those bounds. Okay, so now that I wrote that those were x bounds, I'm okay. But we should have corrected that to begin with. So let's just do that now. All right, so what do the bounds become? Well, we plug in 0. Cosine 0 is 1. Plug in pi fourths. Cosine pi fourths is root 2 over 2. Then we have a minus. Okay, so there's a minus in the front. And we have a 1 over u plus e to the u du. And at this point, you're probably like, why is there a minus? It doesn't feel like the answer should be negative because these are positive functions. We're going over 0 to pi fourths. Well, 1 is actually bigger than root 2 over 2. So these are kind of in the wrong order. Now, wrong I put in quotation marks because it's really up to you as to how you do it. It works out either way. But let's go ahead and just flip the bounds, get rid of the minus sign. Just it'll make us feel better. Well, it'll make me feel better. So this becomes integral. And when you flip the bounds, the minus goes away. Root 2 over 2 to 1 of 1 over u plus e to the u. All right. With all of that done, let's actually integrate. Okay, so the integral of 1 over u is log of u. Integral of e to the u is e to the u. And evaluate from root 2 over 2 to 1. When we're doing definite integral, no need for c's. You might say, don't I need to go back? Because when we were here, we said, we got to go back to x. Do you have to go back to x here? If you've updated your bounds, no, you don't. It's the nice thing about definite integrals. It's a one-way street. You just keep going forward. If you didn't update the bounds, yes, then you got to jump back. All right, so we plug stuff in. Log of 1 is 0. We won't even write it. E to the 1 is e. So then e, subtract, log, root 2 over 2, plus e to the root 2 over 2. And, well, you could do some simplifying, but it's hard to know what they're looking for exactly. And this is a lovely answer, so we stop there. Fun problem, fun problem. All right, almost done. Let's finish it up. Our final problem, we made it. Number 7. Find the function y that solves the separable differential equation. dy dx is equal to y times 4x cubed plus 6x and satisfies that y of 1 is 5e to the 4th. And it says your final answer needs to be an equation that takes the form y of x equals Now, separable differential equation. This is fun because there's really 3 steps. There's the first step, it tells you, is to separate. And so we say, okay, great, we will separate. The second step is you integrate. And, okay, that sounds good. Separate, integrate. What's the last step? Well, then the last step is what I call uncomplicate. Well, of course, the problem is I couldn't come up with a good word that rhymes with 8, so we made up a nonsense word, but that's okay. So we have a plan. Separate, integrate, uncomplicate. Now, uncomplicate, solve for y, get your constant. So what does it mean to separate? Well, it says you're going to put all the y's on one side, all the x's on the other side. Right? So we're separating the variables. So I'm going to think of the dy and the dx as actually disconnected. So we can write this as 1 over y dy, so we move the y across and move the dx across, is equal to 4x cubed plus 6x dx. Step 1 is done. Separation complete. So where to next? Step 2, which is to integrate. So we integrate, and integral of 1 over y dy is log of y. Integral of 4x cubed plus 6x, well, okay, that's x to the 4th plus 3x squared plus c. Don't forget you need one c. They might say, didn't I need a c here? No, you just need one, because you can combine them together into a single constant. All right, and of course, hopefully the 4x cubed to x to the 4th and the 6x to 3x squared, no big surprises. So the integral of x is a half x squared. 6 times half gives 3. Now, there's two things left. We've got to get y by itself, and we've got to solve for c. So this part here, this is an initial condition, and this is going to give us c. Now, the question you might say is, all right, when do we use it? The answer is when it's convenient. So we say, okay, if I plug in y is 5e to the 4th and x equals 1 right now, does that look like it'll be easy to solve for c? I don't like logs, so let's hold off. We'll wait to solve for c. All right, so let's get rid of the log, okay? Because we need to get y by itself. We know we have to get y by itself because it tells us we need y equals. That's log of y. To get rid of the log, we're going to use exponentials. So we get y is equal to, and here's a little bit of magic. So I'm going to write it down, and then I'll say where things came from. X to the 4th plus 3x squared, and a constant there. Now, what was the thinking? Well, here, this is really ex to the 4th plus 3x squared times e to the c. Because addition becomes multiplication. So addition upstairs becomes multiplication. And now, if I take e to a constant, oh, this is a constant. So let's just change the name. So that's changed it to the letter d. It's not the exact same constant as c, but it's essentially saying, here is where our constant has moved to. All right, well now, say, what if we plugged in x equals 1 and y equals 5e to the 4th? That feels a lot better. Okay, so let's do that. So we're going to use our initial conditions. So y of 1 equals 5e to the 4th. Well, that's going to be equal to d. E, upstairs we get 1 plus 3. Well, notice that's e to the 4th. There's an e to the 4th. So that tells us that d should equal 5. So we end up with y is equal to 5e times x to the 4th plus 3x squared. Life is good. Life is wonderful. We have our answer. It's great. So when you're faced with a separable differential equation, just remember your 3 steps. Separate, integrate, uncomplicate, and life is good. When you solve for c when it's convenient. You can do it at the start or hold off. Just do it when it makes sense for you. But that's it. Our last problem. We made it all the way through, end to end. What a fun test, and I hope you enjoyed it, and I hope you're going to do great on the test coming up. All right. See you later. Bye.